Hello friends, in this video I am going to discuss about the flow of viscous fluid through circular pipe, which is nothing but Hagen-Poiseuille law. This particular topic belongs to a module called viscous flow in applied fluid mechanics. Talking about viscous fluid or viscous flow, the viscous flow is nothing but the flow of a fluid which contains very high amount of viscosity, or in other words you can say the flow of the fluid which will flow in very less amount of velocity. So that fluid will try to flow in terms of layers. So this is the case what we are going to consider in this topic, when the flow of this viscous fluid will try to flow through a circular pipe. Let us just now consider a small cylindrical pipe section of radius capital R and a small concentric cylindrical fluid element ABCD, let's say of radius small r, length dx, and let's now locate it at a distance y from the boundary of the pipe. So if this is the case, if we consider the various forces acting on the fluid element, so as you know, when the fluid is in motion, the various forces were going to acting on the fluid, and the various forces we have already discussed in the viscous flow. In this particular case, the forces that were going to act on the fluid element are, the first one would be the pressure force, and that is on the face AB on the left hand side, and that would be in the direction of the flow. So this force is given by P into pi r square, as you can see in this force listed here. The another same force, which is nothing but the pressure force, but onto the opposite side of the element, which is face CD, and that would be equals to P plus curly P by curly x dx into pi r square. Now these two pressure forces are due to pressure intensities on this face AB and face CD. The another force that we are going to act on this fluid element is the tangential force, or in other words it is also termed as the shear force. Now as we all know that when this fluid flow is moving in terms of layers, as we have discussed that this is the viscous fluid flow, and viscous fluid flow contains very less amount of velocity, so the fluid slides relatively to the adjacent layers, and due to this the tangential or shear stresses are developed in a moving fluid, and this tangential stresses induce a frictional force which tends to retard the motion of the fluid particles, so that would be in the opposite direction of the flow. So this force value would be equals to tau into 2 pi r into dx, and that will act on the surface of the fluid element. So these are the different forces now we have considered in this fluid element in the direction of the flow. Now let's try to understand that these forces are acting on this x direction. There are no forces acting in the y direction. So for equilibrium, let's take the summation of this pressure and shear forces in x direction and equating with it is 0. So in other words, nothing but we are talking about summation of these different forces in x direction, taking or equating it to 0. What we can say? We can write it in this way: first P into pi r square minus P plus curly P upon curly x into dx into pi r square, and the tau into 2 pi r into dx, and this would be equals to 0. So this is the forces we are going to resolve in this direction. Now as you know, the sign convention we have considered as the forces acting or either into the right direction or into the left direction. Right direction is nothing but which is the direction of the fluid flow, as you can see in this figure, the flow, and the minus signs indicating the force acting on the opposite direction of the fluid flow. So this pressure intensity, the second one, and the shear stress or shear force will going to act in the opposite direction of the fluid flow. So after resolving or solving this particular equation, what one can say, the first term, which is nothing but P pi r square would be going to get cancelled, and the term which is going to remain is minus curly P upon curly x dx into pi r square minus tau into 2 pi r into dx equals to 0. So we can further simplify this equation. We can take this minus term onto the right hand side. So further simplifying this equation, the final form is going to be look like in this way: tau is equals to minus curly p upon curly x into small r by 2. So now this equation what you are seeing here, let's say, or giving this equation as equation number 1, this equation is showing, or it will give the variation of shear stress across the section of the pipe. So the equation, if you observe properly, so the shear stress tau varies linearly with radius of the pipe, and we can also have this shear stress distribution diagram. So let's say this is the pipe section, and if this is the center line of the pipe, what we can say, the shear stress is varying linearly. So at the radius small r equals to 0, the shear stress would be equals to 0, because as you can see this equation, if you put r equals to 0, when there is no small r is available, the shear stress would be equals to 0. And that is how the shear stress will vary from the center of the pipe to the boundary of the pipe, and it will try to increase as you move away from the center towards the boundary of the pipe. So this particular way, this diagram is nothing but it will give you the shear stress distribution. And if you see here, we can write it in this way: at small r equals to 0, your tau is also 0, that is in the center of the pipe here. And as you move away from the center, which is nothing but when your small r, let's say, will become equals to the radius of the pipe, that is capital R, then this would be equals to tau is equals to tau maximum, because it will give you the maximum value of shear stress. So shear stress value is maximum at the boundary or the surface of the pipe, and it will try to decrease as you move away from the boundary, and it will become 0 at the center of the pipe. So using this condition, when small r is equals to capital R, we can also get this formula for tau max. So tau max would be equals to minus curly p upon curly x into bracket capital R by 2. So this is the case of shear stress distribution. Similarly, we can also get the velocity distribution across the pipe section, and for that what we have to do, we have to use the law of viscosity, which is nothing but the Newton's law of viscosity we can utilize. So now we will try to see the velocity distribution using the Newton's law of viscosity. What one can say, the Newton's law of viscosity will be given by tau is equals to mu into du by dy. So in this term, if you see, the u or small u is nothing but it is the velocity at distance y from the pipe surface or from the pipe wall. And as per this figure what we have considered in our case, what we can see here, the small y is nothing but it is the difference of the capital R minus small r. So from this figure one can also write that this small y is equals to capital R minus small r, and here your u is nothing but it is the velocity. So if you try to take the value of dy, then so it will be equals to dy is equals to minus dr. We can substitute this value of dy into this equation of tau. So what we can get, we will get this way, your tau is equals to minus mu into du upon dr, right. So we can also substitute the value of tau from our shear stress distribution equation, and we can further simplify this equation to get our velocity distribution. So what we can do is substituting this value of tau from this equation number 1 into this equation of this tau, substituting substituting value of tau from equation 1, what we can say? We will going to get the final form like minus mu du upon dr is equals to minus curly p upon curly x into small r by 2. In other words, we can also write this equation in this way: du upon dr is equals to 1 upon mu curly p upon curly x into small r by 2, because this minus will become positive, right? Now, we want to get the velocity distribution, which is nothing but we want to calculate the value of u. So, we can get this value by having integration of this equation, and since this curly p by curly x is not a function of small r, because we are going to take this integration with respect to small r, what we can say, this equation, or rather we can say taking the integration right, we can write it this equation in this way. The first will be u is equals to, this r will become r square by 2. So, 2 is 4, 1 upon 4 mu curly p upon curly x into r square plus c. So, here this is the equation we are going to get for our velocity distribution, but here if you see, this capital C is nothing but is the constant of integration, and now which can be evaluated using some boundary conditions. So, what boundary conditions we can say? Now, you can see here that when using boundary condition as small r equals to capital R, if you try to put these values, when your small r equals to capital R, your u would be equals to 0. Why it is so? Because at the pipe wall, velocity is 0, and if you try to put this condition into the equation, we can get the value of integration constant. Therefore, capital C is equals to minus 1 upon 4 mu into curly p upon curly x into capital R square. Now, we can try to put this value of constants of integration C into this equation number 3 to have our final form. Therefore, the equation of u will become equals to 1 upon 4 mu minus curly p upon curly x into bracket capital R square minus small r square. So, this is the equation which will give you velocity distribution across the section of this circular pipe. And now, if you see this equation is saying that the velocity of the fluid flow varies parabolically, and the surface of this velocity distribution is nothing but paraboloid of revolution. So, this equation, let us say this equation is equation number 4, we can now try to show the velocity distribution across the section. So, if this is the pipe and if this is the center line of the pipe, as per this equation your velocity distribution is parabolic. So, you will get the maximum velocity at the center of the pipe, which is nothing but u max. and as you move from the center towards the surface of the pipe, your velocity will decrease. So this is your velocity distribution diagram. Also from this diagram we can try to find out the value of maximum velocity, which is nothing but u max, and this u max will occur when your small r is equals to 0, which is at the center, right. So substituting this condition, your u max will be equals to 1 upon 4 mu into minus curly p upon curly x into r square. So this is how one can get the shear stress distribution and velocity distribution across the section of the pipe, and this is the case. Now also we're going to discuss about some few more topics. Now we'll try to find out the average velocity. The average velocity is generally obtained by dividing the discharge of fluid across the section by the area of the pipe. So what we can do is we will try to see this figure again to understand more about this average velocity. Let's consider this elementary this concentric cylindrical fluid element is, let's say, now passing through some elementary ring of thickness, let's say dr. So this second figure, this is small b, is nothing but the ring they are showing having thickness of dr, and which is now placed at a radial distance of small r from the center of the pipe. So the discharge through this particular cylindrical ring we can get simply as for average for u average, which is nothing but average velocity, the discharge dq we can say is nothing but is your u into area sum dA. So this area is nothing but it is the area of this cylindrical ring what we have considered. So we can further simplify this equation by this, dq is equals to u into 2 pi r into dr, which is nothing but the thickness of this cylindrical ring. So what we can do is we can also try to substitute the value of this u velocity from this equation number 3. So what we can get from this equation, therefore this discharge dq is equals to 1 upon 4 mu minus curly p upon curly x into capital R square minus small r square into 2 pi r into dr. So what we have to do, we want to get the value of this discharge q. So we need to take the integration on both the sides. So taking integration on both the side, what we can write, and q is equals to, the common term will come out of the picture. So if you see here, this 2 2's are 4, so pi upon 2 mu, pi upon 2 mu into minus curly p upon curly x, which will come as a outside from the integration because they are the constant terms. Integration from 0 to capital R of small capital R square minus small r square into r into dr, right. So further simplifying this equation, we can write it as q is equals to pi upon 2 mu bracket minus curly p upon curly x into r square into small r square by 2 minus r raised to 4 by 4, putting limit as 0 to r, and now applying this limit we can further get this equation as q is equals to pi upon 2 mu minus curly p upon curly x bracket r raised to 4 divided by 2 minus r raised to 4 divided by 4. So, the final form of this equation is q is equals to pi upon this 4 will come as a common in denominator, which will multiply by with the 2. So, it will becomes pi upon 8 mu into minus curly p upon curly x into r raised to 4. So, now this is the equation of discharge, and what we have to do, we want to calculate the average velocity. So, you are getting this average velocity, we need to divide this discharge by the area. U AV is equals to Q divided by area, right. So, what is Q? As we have just found out into this equation, pi upon 8 mu bracket minus curly p upon curly x into r raised to 4, and what is the area of the pipe, which is nothing but pi into r square. So, this r square r raised to 4 will get cancelled, so here it will become r raised to 2. So, therefore, this equation will look like u average is equals to 1 upon 8 mu, because also this we can get rid of this pi as well, 1 upon 8 mu minus curly p upon curly x into r square. So, this equation will give you the idea about average velocity. Now, what we can do, we can take the ratio of this maximum velocity to average velocity to understand the relationship between these two different velocities. So, dividing this equation of average velocity with your equation of maximum velocity. So, taking the ratio of maximum velocity to average velocity, u max divided by u average is equals to 1 upon 4 mu minus curly p by curly x into r square divided by 1 upon 8 mu bracket minus curly p by curly x into r square. So, if you take this, the final term will become as u max to u average is equals to 2, or in other words you can write it in this way, u max is equals to 2 times u average. So, this is the relationship between the maximum velocity and average velocity. The maximum velocity is 2 times the average velocity, right. So, we can also get the location where this local velocity will become equals to the average velocity, right. What we can do, that this equation of u max now we can use to get this location where this velocity, which is nothing but your u value or the local velocity u, would becomes exactly equals to this average velocity. So, what we can do here is location where this local velocity, or in other words simple velocity, is equal to average velocity. So what we can do is the equation of local velocity, we have just discussed above the u equation, which is nothing but the equation here. We as know u is equals to 1 upon 4 mu minus curly p upon curly x bracket r square minus small r square, right? And this equation now can be divided by the maximum velocity, which is nothing but u max. So dividing by u max, what we can say, this u upon u max would be equals to r square minus small r square divided by capital R square, because u max we have just discussed, u max is nothing but is your 1 upon 4 mu minus curly p upon curly x into capital R square. So this term will going to get cancelled, so final term would be going to look like this. So in other words, your u will be equals to u max into bracket, we can also write this term as 1 minus small r upon capital R whole square, right? Also we can use this relation between the average velocity and maximum velocity, which says that your u average is equals to u max divided by 2, or in other words, u max is your 2 times the average velocity. So since we just wanted to find out where this local velocity will become equals to the average velocity, we can write in this way, since your u, we are going to make it as the average velocity, this equation can be further written as u max by 2 is equals to u max into bracket 1 minus bracket small r upon capital R whole square bracket close. So we can get rid of this u max from the both the side. So this equation will going to look like this: 1 by 2 is equals to 1 minus r upon capital R whole square. Therefore this r upon capital R whole square is equals to 1 by 2, or in other word, this small r is equals to, if you finally simplify this term, the final value I have calculated, it will become is equals to 0.707 capital R. So this equation reveals that the local velocity will become equals to average velocity of flow, that is UAV, at a radial distance of 0.707 of capital R from the center of the pipe. So this is how one can able to get the location where this velocity will becomes to average velocity. Up till now, what we have discussed is the prerequisite for the Hagen-Poiseuille law. We can also get this Hagen-Poiseuille law by having the pressure drop in terms of the average velocity, right? So what we can do is we can try to go for calculating the pressure drop in terms of the average velocity to finally get our Hagen-Poiseuille law. So the pressure drop in terms of average velocity, what we can do, so we can use that equation of average velocity only, because since we are getting this taking this pressure drop in terms of average velocity, we can use the equation of average velocity. U average is equals to 1 upon 8 mu bracket minus curly p upon curly x into r square. So we are interested in pressure drop now, so we can try to get this equation in terms of minus curly p upon curly x is equals to 8 mu u average divided by capital R square. So now for this, when we are going to determine the pressure drop, we should have the length of the pipe. So we have to consider the length of the pipe as a finite one. So let's just try to consider the length of pipe as capital L. So what we can do is, your pressure drop from one side to another side, which is nothing but P1 minus P2 with respect to the length of the pipe, would be equals to 8 mu U average divided by R square. So did you understand what we have done? This minus curly P by curly X is nothing but is your pressure drop, and this pressure drop can be further written as P1 minus P2 with respect to the length of the pipe, like this. So if you do this, what we can say, your P1 minus P2 will become equals to 8 mu U average into L divided by R square. We can also write this equation in terms of the diameter of the pipe instead of the radius. So what we can write here is, your P1 minus P2 is equals to 32 mu U average L upon D square. This 32 is nothing but is just because your R is D by 2. So if you substitute R as equals to D by 2, so it will become equals to D square by 4, and that 4 will be multiplied by with the 8 in numerator, so it will become 32, right? So this equation is, now you can see here, is equation which shows the pressure drop in this section or in this case. What we can do is, we can try to further simplify this equation in terms of the equation of head loss, because we are also interested in what would be the pressure drop or the loss of head or pressure has occurred. So we can try to further simplify this equation in somehow that we can try to multiply with this pi by 4 d square, which is nothing but the area of the pipe in numerator and denominator both. So if we do that, that means the multiplying with pi by 4 d square both in numerator and denominator, this equation will be equals to P1 minus P2 is equals to 32 mu U average into pi by 4 d square into capital L divided by d square into pi by 4 d square. So if you see here, this is the area in numerator, pi by 4 d square, right? And this particular case, if you see here, so it will be comes to, let me write in this way, P1 minus P2 is equals to, this 4 will come into this numerator, so it will be multiplied with 32, so it will be equals to 128 into mu into U average. This numerator pi by 4 d square, we are going to write it as, we can try to write it as area of the pipe into length of the pipe divided by pi into d raised to 4 in denominator. Now this area and U average velocity, if you know, we can try to write it as a discharge. So this P1 minus P2 is equals to 128 mu into Q divided by L pi into T raised to 4. So loss of pressure head is nothing but given by the HF term. So loss of pressure head is given by HF is equals to P1 minus P2 divided by gamma, because according to Bernoulli's law, this loss of pressure head is always in terms of specific weight gamma. So substituting the value of P1 minus P2 into this equation, what we can write it as HF is equals to 128 mu into Q into L divided by gamma pi T raised to 4. So this final equation, maybe equation number 7, is nothing but is known as your Hagen-Poiseuille equation, and this is the equation which is now used for viscous flow in circular pipes. Don't forget to mention that this gamma in denominator is the specific weight of the flowing fluid, right? So if you remember that in case of pipe flow, this same equation of this HF, this is the loss of head due to frictional resistance in the pipe only, given by Darcy-Weisbach formula, which is similar to this equation. So we can try to find out the relation between these two equations as well. How we can do it? So if you try to equate this particular two equation, because this equation, Hagen-Poiseuille equation, is nothing but it will give you the loss of head due to frictional resistance or the pressure drop, but it is the case of viscous fluid. And in case of Darcy-Weisbach formula, we haven't considered this viscous thing or viscosity onto the picture. Instead, we have considered the frictional factor F. So we can try to equate these two equations and we can get the equation of frictional factor. So if you remember, in Darcy-Weisbach formula, we were having that analysis that friction factor value can be found out by using the value of Reynolds number, and that equation was, so if you remember, the F is equals to 64 by Re and like that. So if you equate this Hagen-Poiseuille equation with the Darcy-Weisbach equation, we can get the equation for the friction factor small f, and it would be equals to 64 by Re, right? So thus this value of friction factor can be computed by the comparison of these two particular equation, right? So this is how the case of this viscous flow through a circular pipe, which is Hagen-Poiseuille equation, can be studied. Further, we can also try to solve these certain examples based on this equation to finally understand the application of this equation, how you can use this equation in various categories of examples, right? So what that will do in next lecture. So in next lecture, we'll try to solve few examples based on this Hagen-Poiseuille equation, and finally we'll try to understand this law very properly.